So let's go ahead and continue on with example number 1, jumping on to part B. Let's see what this question asks. What is the probability of having to wait over 5 minutes for the next customer to arrive? Well, since I already have my variable identified up here, and I'm still asking the same question, how much time does it take for the next customer to arrive? And I'm still measuring in the same unit of time, which is minutes, then I don't really have anything to change, except my picture and my probability setup. So let me go ahead down here and draw out a quick picture of what I'm working with. So I'm going to draw out an exponential distribution. I still have my variable of y, which stands for the number of minutes I have to wait. And then on my axis, I can realize that now I want to go from 5 and up. Well, if I just look at this, one thing I should be able to determine immediately is that it would make a lot of sense if this probability was going to be smaller than the probability I calculated above in part A, because I should have shaded less total area underneath this curve. Well, let's go ahead and calculate this out and see if what our intuition tells us is going to actually line up with the calculation. So we want the probability that y, the amount of time we have to wait, is more than 5 minutes. Well, I know that again I'm going to have to do e raised to the power of negative of this number multiplied by lambda. Remember, lambda has to have the same units, which it does here. So I'm going to multiply this by 1.2. Now I can just go ahead and type this into the calculator directly. I don't even have to simplify down what I have here. Let me just go ahead and type that in. So I'm going to have e to the negative 5 times 1.2. And when I hit enter, here's my probability. And in fact, yeah, it is a lot smaller than the probability we got before, 0.0025. So I'm going to go ahead and write that value down, 0.0025. So I can see that even as I change this value that I'm going to put on the axis, as long as the units maintain the same, or are maintained, then I don't really have much to change about the question. Well, let's take a look here at part C. This one's kind of interesting. What is the probability of having to wait between 2 to 4 minutes, that's good, everything's staying the same, for the next customer to arrive? Okay, well, I know that I can draw out my exponential distribution again. I'm still dealing with that same unit of time, which is minutes. And now, on my picture, I can see that I want to be somewhere between 2 and 4. I'm just kind of eyeballing where those numbers would be on the number line. The picture is just to help me kind of think through what I'm working with. Well, this is kind of strange because how do I get this? Notice that, again, since I'm not using any sort of like fancy calculator command, I don't have any spot in a formula to input like a starting point and a stopping point. The probability distribution of the exponential and the way that I calculate the probability for it only allows me to go from a number to the right. I only have the ability to calculate being above a particular value. So how in the world am I going to get this area that exists between two values? Well, I'd like to propose the following. What if I was to imagine, instead of just shading this area, what if I shaded all of the area that existed above 2? All of it. If I shaded all of that area, we should admit that that is way more area than what I wanted to shade, because I only wanted to shade what was between 2 and 4. However, if I could simply kind of subtract off or erase the area from 4 and up, I would be left with exactly what I want. So I'm going to go ahead and try to write it out like this. I want my value of y to come in between 2 and 4. And I can get that by finding all of the area above 2, which is again way more than I want. That's shading all of my area here, way more than what I'm looking for. And then I'm going to subtract off of that all of the area that is above 4. So I'm essentially going to come in and erase that portion. Well, that leaves me with what I want. And these are both areas being measured from the right of a number. And so I know how to measure each one. The first one's going to be e to the negative of 2 times my value of lambda. And my other probability is going to be e to the negative of 4 times the value of my lambda. Now I can just go right to the calculator and type both of these in, and I should be able to get to my final answer. So let's see what we come up with. I'm going to do e, this is negative 2 times 1.2. Then I'll do minus e to the negative 4 times 1.2. I can just type all of this in automatically, and I get to a final answer of 0.0825 if I round to those 4 places. So 0.0825. So finding the area between two values isn't that difficult, but I do have to be a little bit creative with how I come up with that calculation. So this might take a little bit of practice, which is why immediately right now I'm going to recommend that you definitely go practice a lot more of these sorts of questions using the worksheets. So that way you can see this type of question occurring numerous times and get comfortable with answering it. Now before we end this video, we're going to take a look at one final question that may occur here, which is, how much time should the bank expect to have to wait between customers? That is, I want to know the average wait time. Remember, whenever we see that word expect, we associate it immediately with I want an average. In this case, I want an average of y. Well, the nice thing is that if I was to go look at the formula sheet or at the box up here, I can see that to calculate the average and also the standard deviation, I have not only the same formula, but actually a really easy formula. I just take 1 and I divide by the value of lambda. Now I'm going to go ahead here and do my division while also considering some units. So notice here, if I'm going to do 1 divided by lambda, that's 1 divided by 1.2 customers per minute. Now when I go ahead and I think about simplifying this, you'll notice that one thing I could do, since I'm kind of dividing by this fraction, is I could imagine rewriting this as 1 over 1.2, and then on the side I could rework this as minutes per customer. Notice I'm just multiplying by the reciprocal, the same way I would always do the division of fractions. So I can just go ahead and go to my calculator to figure out what is 1 divided by 1.2. Well, let's see what that looks like. 1 divided by 1.2 comes back at about 0.8333. So what this tells me is that I'm going to have an average wait time of about 0.8333 minutes per customer. That is, how long should I expect to wait? About 0.833 minutes for every customer. So if you ask, what is 0.833 minutes? Well, remember that if you took this value and say multiplied by 60, there's 60 seconds in a minute. That would kind of be the equivalent of 50 seconds per customer. So I'll just go ahead and leave an extra note here that this equates to about 50 seconds per customer. You don't necessarily have to make these sorts of simplifications and changing the units of time. I'm just doing it here so I can maybe make a bit more sense of what this 0.833 minutes really means. So I'm saying, hey, not too surprising. It's pretty common. It's the most typical to wait about 50 seconds for a customer to arrive. Okay, so we'll go ahead and take a look at some more examples of exponential distributions in example 2, which we'll cover in the next video.